Okay, so we are looking at utility maximization today and microeconomics. Microeconomics theory. Unlike the normal principles of microeconomics, the theory may deal more with functions than numbers. But if you're able to get the understanding for everything, you'll be able to go through, be able to use numbers to solve. So, under utility maximization, what is utility? Utility is believed to be the satisfaction that one derives in consuming a particular commodity. So, when you consume like the satisfaction derives in consuming a particular commodity. In this case, we'll assume that an individual consumes two commodities, say X and commodity Y. And we believe that you can only spend when you have something in your hands. So if you don't have money, you cannot spend. So we believe that the individual will spend his income on commodity X and commodity Y. So they are the commodities that let's say the individual is looking at. So we look at maximizing utility. Everybody wants to maximize the satisfaction they derive for consuming a particular commodity. And in terms of selling, producers also seek to actually minimize their cost of production. So in terms of utility, you look at maximizing the utility. In terms of cost, we look at minimizing the cost of production. So we are going to now consider utility maximization. How do we maximize utility? Or how can we find the maximum demand function under utility maximization? And then under that we have the Marshallian demand. So we look at the Marshallian demand function. Marshallian demand function. So look at the Marshallian demand function. That's so now we have to know how to find the utility maximization. Normally, they use two steps of approach. We have the MRS approach, that is the marginal rate of substitution. So MRS. We have the MRS approach, and we have the Lagrangian approach. So you can use either the MRS approach or the Lagrangian approach to maximize your utility. So we'll first go through the MRS approach, and then we'll also look at the Lagrangian approach. So with the MRS approach, I said that now we have our U representing the utility, and then we believe that the individual consumes only two commodities, so X and Y. So you have UX, then you have UI. So marginal rate of substitution. The word marginal tends to be a change. So if there is an extra thing, something like a change. So in this case, you apply differentiation. So you find change in U. So let's say the U, and we have MU. We are differentiating this MU. We differentiate with respect to X because of the X. So we differentiate U with respect to X. So MU X dx. And then we have MU Y. Then we differentiate with what? Y. Now, the first derivative, it is for minimum or maximum. The first derivative is believed to be equal to 0. So for minimum or maximum differentiation, the first derivative should be equal to 0. The first derivative is said to be necessary, but not the sufficient condition. So the sufficient condition, you have to find the second derivative, but now we are only looking at the first derivative. So let du be equal to 0. So you have 0 is equal to mux dx plus muy dy. Then I'll bring this one there to get negative muy dy equal to mux dx. I want to make dy dx the subject. So change your subject. How do I make dy dx the subject? I have dy here, I have dx here. So if I divide through by dx, I'll have dy dx. Then this one will go. Then I'll have mux standing alone. But I'll still have muy multiplying the dy dx. I have to get rid. So I'll divide by muy on both sides. So simple, to do it simple, I'll divide both sides by both sides by muy dx. So that I have minus muy divided by muy dx equals mux dx muy dx. So this is x cancels this is x. This muy cancels this muy. Then I have minus dy dx equal to mux over muy. So we have a negative dy dx and then the mux muy. This is the MRS. Now the MRS is actually a negative slope. So something like when I have my u and I have my x here, and I've had the change the mu. So the negative side is depicting that indeed the MRS is a negative slope. So this marginal rate of substitution, you are substituting x for y. So that's what you get, mux over muy. Okay. But assuming I have an income function, or let's say the budget constraint, because under utility we believe that the consumer is consuming subject to the income of the consumer. So we draw the budget constraints. So the income function here. The income is, let's say, px, x plus py, y. Okay. Similarly, when we also differentiate this one, we'll end up getting dy dx being equal to px minus dy dx will be equal to minus px over py when you differentiate. Get something simple. So at equilibrium, so where the indifference curve touches the income, your income function or the budget function, you have this as this. So we equate mux over muy will be equal to px over what? Py. Someone may write it as mux over px equal to muy over py. So with the MRS approach at equilibrium, at equilibrium, you have either this or you can write as this. So when you are asked to find the Marshallian demand function, you can go by the equilibrium point of the MRS. So you can just put this and then you work the function down. We will go through it. So this is the proof of the MRS and for the equilibrium. So we'll go through the Lagrangian approach also. Or first, let's solve a question with the MRS approach. We'll solve a question with the MRS approach. And then we'll go through the Lagrangian approach. Lagrangian approach. So given that u xy is equal to x alpha and then y beta subject to I equal to pxx plus pyy. Find the Marshallian demand function for x and for y. So we can use either the MRS or the Lagrange. Now because we've done the MRS, we are going to go to the MRS approach. So we know for MRS, solution, for MRS at equilibrium, your MUX over MUY is equal to PX over what? PY. So we have to find MU with respect to, so we differentiate the U with respect to X, we differentiate the U with respect to Y. So now MUX will be equal to dx of UXY. So this one is step-by-step approach. So we are differentiating this with respect to x, means that y will be held constant. By differentiation, we know that when I have something like ax exponent n, differential of ax exponent n with respect to x gives me an, so I'll multiply this by this, then x, I'll subtract 1 from the exponents. So an x n minus 1. So with this one, this is held as constant. So we will not differentiate with respect to y, but we are differentiating with respect to what? X. So now the coefficient of x is, let's say, the constant. 1 times the constant, 1. And the exponent is alpha. So in that same approach, you have alpha x, subtract 1 from the exponent, x, alpha minus 1, now I have y exponent beta to be the derivative of the u with respect to x, so that is the mux. So similarly, you find the muy. So muy becomes dy, we are differentiating this with respect to y, that is x alpha y beta. This gives us beta x alpha y beta minus 1. Let this be equal to equation 1. Let this be equation 2. The moment we have this, we can substitute it into the equilibrium point. So I'll write my equations out for mu x is equal to alpha x alpha minus 1 y beta. So mu y is equal to beta x alpha beta minus 1. You should know this is the Coplot function. So you can use the Serre's function or Lantieff. You can also use the fixed proportion function. So at the equilibrium, you have this. Equation 1, equation 2. So I'll put my 1 there, which was alpha x, alpha minus 1, y beta over beta x alpha, y beta minus 1 equal to px over py. At this point, we can make either x or y the segment, but we have to simplify. So we apply indices. With multiplication or division. When I have a over b times c over d e f, it can be written as a over d times b over e times c over f. So with this concept, I will try and split this to look like something like this. So I have alpha over beta times x alpha minus 1 x alpha times y beta over y beta minus 1 equal to bx over by. So now I can treat this, solve this very easy, in an easy way. If I have a exponent n divided by a exponent m, according to the laws of indices, I can write it as a n minus m, according to the laws of indices. So I will apply it here. When I apply it here, I'll get alpha over beta times alpha, so x minus 1 minus alpha, following this, times y beta, the minus, so to be minus beta minus 1 equal to bx over by. This will cancel this. So I have alpha over beta, x exponent negative 1. Then when I remove the bracket, I have beta minus beta, then plus 1. So I have times 1 y equal to bx over py. Okay. The same indices. When I have 1 over a exponent negative n, it is the same as a exponent n. Similarly, when I have a exponent negative n, it is the same as 1 over a exponent n. So now we have x exponent negative 1. So it will be represented as, or written as 1 over x. So I have a alpha over beta times 1 over x times y equal to bx over by. So then I'll have alpha y over beta x bx equal to bx over by. I want to make y the subject. So I would have to first multiply through by, I'll get rid of the fraction here. So I'll multiply through by beta x. So I'll multiply through by beta x times beta x. This will cancel this, and I have beta x multiplying this. But there will be alpha. So I have to come and divide by alpha. So simple, in a simple way, I'll say multiply through by beta x over alpha. When I do that, I get rid of the alpha and the beta x. So now I have beta x over alpha multiplied by alpha y beta x equal to bx over py times beta x over alpha. So this alpha cancels this alpha, bx cancels bx. So I have y is equal to beta px x over alpha py. That is a function for y, but that is not the demand function for commodity y. You have to take note. For utility maximization, the demand function should be expressed in terms of the income, in terms of the proportion of the commodity. In this case, if it is about x, alpha is the proportion at which it is consumed, or let's say half. So the demand function should be in terms of this alpha, the income, and then the price of x. That is for x. When we take for y, the demand function should be in terms of the beta here, the price here, and the income. Take note is for the Douglas function. We have not tried for Lentief or the fixed proportion. So I'll clean this. So now that I have the function for y is going to be beta px alpha py, I'll put this function into the income function. So now my income will be equal to px times x plus y. In place of the y, I'll put the function there. Beta over alpha px x over py. This py will cancel this py. Then I'll get I equal to px x plus beta over alpha px x. I want to get rid of the fraction here. So I will multiply the whole equation by alpha. So I have alpha I equal to alpha px plus times x, then I'll have beta px x. In mathematics, when you have y plus y, the answer is 2y. It's 2y because we assume that the coefficient is 1 and 1, so it's actually 1 plus 1, which gives me 2y. In this case, px and px are the same, so I'll add their coefficients to get alpha plus beta, then px x alpha I. But alpha plus beta is supposed to be equal to 1. So if it is equal to 1, I have alpha I equal to px times x. So when I want to make x the subject, I'll divide 2 by px. When I divide 2 by px, I'll have x equal to alpha I divided by px. And that will be the Marshallian demand function for commodity x when we are using the Cobb-Douglas function. So we now have the Marshallian demand. So normally you see xm, you see x exponent, and when you see x exponent xm, it is the Marshallian demand function for commodity x. So it is now alpha I over what? Px. We put this one into the function of y that we had. So y was equal to beta over alpha px over py times x. So times x, we put alpha I over px. This px cancels this px. This alpha cancels this alpha. Then we have y equal to beta I over py. So that is the Marshallian demand function for y. So we have used the MRS approach to prove or find the Marshallian demand function for commodity x and for commodity y. So the next one will be the Lagrangian approach.